Let's pick up right where we left off in the last video. We were discussing power series, these infinite polynomials, and considering the domain for these series, which is going to be the set of the x values that the series will converge for. So what values of x can I plug into these infinite series and get back convergence? So here was just a little example of what we had talked about last time. We have three possibilities for what is called the radius of convergence, the radius around the point at which it is centered that this will converge for. So to give us a little visual here, here are three little number lines for x, and here are our three possibilities for convergence. I have to abbreviate to squeeze that in there. So we got three possibilities for convergence. So what are our three possibilities? Well, it could be the fact that we have a radius of convergence that is equal to 0. This is the most restrictive type of convergence for a power series. What this means is that the power series will only converge at a single value, the value at which the series is centered, and that is x equals a in our definition for a power series. So that has it's not even an interval, it's just a single point of convergence. So these power series have a single point, what's called an interval of convergence. In this case, we can't even really think of it as an interval, but that's how we define it when we talk about the domain of these. So we're just going to say it has an interval of convergence at a single point, x equals a, or at the point a. Now, the other extreme, right? That is the most restrictive type of convergence, and then the most open type of convergence is having a radius of infinity, where we literally can cover any value of x, any real number works for convergence. We can plug any number for x in and still have absolute convergence in our series. Okay, so that's a radius of convergence of infinity. Now, the third possibility, of course, is that we have actually a finite radius. So we have some radius r, we'll call it r, and some r value where we can go r to the right and r to the left of our center point, and we can find convergence. That gives us actually four possibilities for the interval of convergence, because what we don't know if we have a finite value is we don't know if the endpoints will converge. We do know that within the interior of that interval we have absolute convergence, but the endpoints actually have to be tested. So those endpoints are still going to have to be tested. We still have to test. So what this means is that we still have to test, still need to test endpoints. So when we're talking about where is it going to converge, well, we can find the interval, the interior of the interval of convergence, and then we just go back and we test those endpoints. Okay, so that's what we're going to spend this video doing, some examples of here's a power series, figure out where it converges, figure out what the radius of convergence is, figure out what the interval of convergence is. So we know for what x values we can work with that power series. And here are some steps, so outlined kind of here in typed form. I just took the steps to find the radius and interval of convergence. Here is our general definition. So given a power series, and we say that this power series is centered at x equals a, and for a visual, kind of corresponds with the visuals we were just looking at. For a visual, we've got our x. You can think of this as the number line or the x-axis. You've got your x value. We're centered at that point A, and then we have some radius of convergence. So here's our radius of convergence. And that radius of convergence goes both to, obviously it's a radius. We're talking about x minus a being in absolute value less than that radius when we talk about a radius of convergence. So that means that the distance of x's away from a can be r. So we can go to the right, or we could go to the left, a distance of r, okay, and create this interval of convergence. Now, the endpoints may or may not converge, as mentioned in the previous portion we were just talking about. So how do we do this? Well, we come across a power series, my highlighted generic version up above. Come across a power series, say where are we centered at? What is our a value? If you want a number line, create a visual. I'm a very visual person, so I like to have the number line. I like to see where my a is, center of that number line, and then I try to figure out, okay, how far can I go? What is my radius? How far can I go away to the left and the right of that point, that center point, and still have convergence? Okay. We will use one of our tests for convergence to determine the radius of convergence. I will say this, the root and the ratio test are really great options. So we'll utilize that root and ratio test quite a bit to find these radiuses of convergence. If the radius of convergence is 0 or infinity, we're done. We got it. We know. Okay? If it's 0 or infinity, we're done. We don't have any more work to do. We would know exactly what the radius and the interval are if that through that test for convergence we come out with the radius being 0 or infinity. Now, on the other hand, it could be that we come out with a positive number. If we come out with a positive number, what we do is we figure out what is the absolute interval of convergence, the interior of the interval of convergence. So this is the interior of, and I'm going to abbreviate here, interval of convergence. Okay, we know on that interior of the interval of convergence, we know that we have absolute convergence, and then all we have to do is test the endpoints. So we use just, again, we go back to all of our tests for convergence. Okay, so all of that buildup, all of those tests for convergence is going to be utilized here. So all of those tests for convergence, we come in and we actually have to test the two endpoints. So we go in and we test the two endpoints. So those are the steps that we're going to go through. I'm going to walk through those steps in a few different examples here, but here they are summarized. So just real quickly again, figure out where you're centered at. Use a number line if that helps you to have a visual. Run one of your tests for convergence, most likely a ratio or a root test. If your radius of convergence comes out as 0 or infinity through one of those tests, then you're done. If not, if it comes out as a positive number, figure out what your interval is, figure out what the interior of your interval of convergence is, and then test those two endpoints to see if you can have, you can include those in your interval. Okay? Because you do end up with 4 different possibilities for your interval of convergence. It's either all open, both endpoints closed, both endpoints included, or it's half open, half closed. Okay, so let's jump right into an example, and it was one that we had looked at in the first video just to see what a power series looks like. So this was one of our examples in the first video where we said, okay, a power series, this is how a power series is defined, and here is what one would look like. So this is what a power series, this is an example of a power series. And the series from n equals 1 to infinity, we got a switch on it. The coefficients are -1 to the n minus 1 over a factorial 2n minus 1 factorial, and x minus pi over 3 to the 2n minus 1. So in expanded form, it looks something like this. So I just started to expand it out so we could see that's what it would look like in expanded form. Okay? So that's an example of a power series, infinite polynomial. What we want to know now, so the question is where, for what values of x, is this a valid power series or a function? For what values of x does this converge? Okay. What is the domain? That's another way to think of it. What is the domain? What are the possible x values for which this infinite polynomial has convergence? Okay. Can come out as a finite sum. So let's do it. So it's obviously centered at pi over 3. So I already started out. I wrote the pi over 3. I wrote the number line. And now we're going to get in there and say, okay, well, what's the radius and radius of convergence and interval of convergence? And to do so, I'm going to run, I see that factorial. I think in my head, factorial. That's a great reason to use the ratio test. So I'm going to say let L be equal to the limit as n approaches infinity of -1 to the n plus 1 minus 1, so just -n to the 1, over 2, let's write it this way, it's going to be 2n plus 1 minus 1 factorial, and in the top here I'm going to move that x minus pi over 3 to the 2, and same thing, n plus 1 minus 1 power, times, and then we're going to have 2n minus 1 factorial over -1 to the n minus 1 times x minus pi over 3 to the 2n minus 1. Okay. Now let's get in here and simplify this a little bit. Clearly, I'm going to go ahead and just show this up here. This is 2n plus 2 minus 1, so this is 2n plus 1. Same thing here, 2n plus 2 minus 1, so that becomes 2n plus 1 factorial there. and the negative ones. Let's go ahead and write it all out. N, limit as n approaches infinity, we're going to have negative 1 to the n over negative 1 to the n minus 1. Those are in absolute value and are going to reduce down to just positive 1. We get a negative 1 to the negative first power, but it's to the absolute value, so we won't need to worry about that. That will become just positive 1. 2n minus 1 factorial over 2n plus 1 factorial, and x minus pi over 3 to the 2n plus 1 over x minus pi over 3 to the 2n minus 1. Now, when I go and I do my reduction here, I will get the limit as n approaches infinity. Again, that becomes just 1 on the outside of the absolute value, so I'm going to pull that out. I'm also going to write the absolute value of x minus pi over 3 squared, the difference of the powers there. I do have to keep the absolute value on that one, although since it becomes a square, I was thinking on the x minus pi over 3 piece, I would have to keep the absolute value. Since it's a square, I could actually drop the absolute value on that portion as well. Now the factorials are positive, and so what we could do here, because n is greater than or equal to 1, what I could do here on the expansion of the factorials is drop the absolute value since they're positives. Couple of notes here. The difference here, there are 2 units, which means there's going to be 2 terms in the expansion of these factorials difference. So I end up with 1 times 2 times 3 out to 2n minus 1. That factorial has 2 less terms than the factorial in the bottom. We get lots of canceling. It will hit the 2n minus 1 term and continue 2n and then 2n plus 1. So we have those 2 additional terms in the expansion of the factorial. So if we wanted to utilize that process as we're doing this, we could. We end up with the limit. And real quick, this is a constant in terms of the limit. So we can actually bring these pieces, any constants can come outside of the limit. And so I'm going to go ahead and do that. That's something we're going to utilize here. This becomes just the absolute value. And again, I'll put the absolute value in red here because we don't need the absolute value, but that's because of the square, not because of the x minus pi over 3. We could actually drop the absolute value since we have a square, so I'll make a little star on that. If we wanted to, we could drop the absolute value. We still have the limit as n approaches infinity of this factorial, the expansion of those factorials, lots of canceling, 1 over, we end up with 4n squared plus 2n, which this is going to grow without bound in the denominator. 1 divided by something that grows without bound approaches 0. And so we basically have x minus pi over 3 squared times 0. I will write that step in just to show that step. But what we end up with for this limit, this L value just became 0. Okay? It's zeroed out. X minus pi over 3 squared times 0 will be 0. So this becomes 0. And if we remember our ratio test says that if this limit is less than 1, we have absolute convergence. Now remember, we're trying to figure out what values of x this will be convergent for. So this is absolute convergence for all values of x. This means that it doesn't matter. So right here, if we let's circle this piece. It doesn't matter what we plug in here for x. X can be anything. X can be anything because in this limit, in this ratio test, doesn't matter what x is, it's going to get zeroed out. It's going to get obliterated by what's left over from the factorials in the expansion of that ratio test. So we end up with this absolute convergence here. This means every value of x works. So you have to really wrap your head around that. The limit itself came out as 0, but what that means from the ratio test, what that means is that our radius of convergence, so our r is actually infinity. Our radius is infinity. Our radius of convergence is infinity. If we go back to our number line, let me zoom out a little bit here. If we go back to our number line, what that's saying is that we can go infinitely in either direction. So this number line means that every single value of x works. Our radius is infinite. Okay? So we can go infinity in either direction. Our radius is infinite. So if our radius is infinite, that means that our interval of convergence, IOC for interval of convergence, I'm going to abbreviate, is from negative infinity to infinity. And that is the end of that problem. Okay? If we end up with infinite or zero, if our radius is infinity or zero, then we are done. We do not have to go any further. So this radius is infinity, and our interval of convergence ends up being from negative infinity to infinity. Okay, so that's our first example. I'm noticing my time, I'm hitting 15 minutes here, and I'm going to go ahead and put the next two examples in a second video so the videos can remain manageable.